If x squared plus y squared plus z squared equals 1, and the value of 2x plus 3y plus 6z is maximized, find the value of x. In this video, we'll discuss two approaches: an algebra-based solution involving the CSI and a calculus-based solution using the method of Lagrange multipliers. Let's begin with the algebra-based approach. We wish to maximize the sum 2x plus 3y plus 6z. Let's consider the square of this number. The Cauchy-Schwarz Inequality, or simply CSI, suggests that the square of 2x plus 3y plus 6z is less than or equal to the product of 2 squared plus 3 squared plus 6 squared and x squared plus y squared plus z squared. The first factor is the sum of the squares of the coefficients, while the second one is the sum of the squares of the variables. Since we are given that x squared plus y squared plus z squared equals 1, the right side of this inequality becomes a constant, which means we can actually find the bounds for 2x plus 3y plus 6z. However, the question we have here actually asks for the value of x that would give the maximum value and not necessarily the maximum value. Hence, we actually need not solve this inequality. Just for the sake of exploring things, let's also try to solve for the maximum value. Evaluate the sum of the constants in the right side and substitute 1 as the value of x squared plus y squared plus z squared. We're left with 49. Using properties of inequality, the solution to this one is the set where 2x plus 3y plus 6z is between -7 and 7 inclusively. Hence, the maximum value is 7, while the minimum value is -7. To be more formal about it, we still need to confirm that the equality holds for a certain value of x, y, and z. So now let's ask the important question: when are the minimum and maximum values attained? For the CSI, equality holds when the ratios of the variables and the coefficients are equal. For this particular case, equality holds when x over 2 equals y over 3 equals z over 6 equals a constant k. We can rewrite all variables in terms of k. Let's run back and note that 2x plus 3y plus 6z can be expressed in terms of k as 49k. Again, we do not need this value, but it will play a part in our reasoning later on. We can solve for k by substituting the values of x, y, and z in terms of k in the given equation. We see that the equation becomes 49k squared equals 1, which we can readily solve. The possible values of k are positive and negative 1 over 7. Since we have previously established that 2x plus 3y plus 6z is equivalent to 49k, we choose the positive value to attain the maximum. If we need the minimum instead, we choose the negative value. Now finally, we know that x equals 2k, and knowing that k equals 1 over 7, the value of x must be 2 over 7, and that's our final answer. In my opinion, this is the best solution for the given problem. For mathletes who are adept in using classical inequalities, this one is a no-brainer. One limitation of this method is, of course, the given conditions must fit the CSI. For example, if we wanted to maximize x squared plus 3y plus 6z instead, we might not be able to use the CSI immediately or at all. Now, the second method is known as the method of Lagrange multipliers. I like this because it's simple to use and can be used for many optimization problems. The thing is, we have to have a background on multivariable calculus. For this method, we will restate the given problem as maximize 2x plus 3y plus 6z subject to x squared plus y squared plus z squared equals 1. The first part is what we will refer to as the objective function, while the second one is the constraint. Denote the objective function as f of xyz and the constant as g of xyz. Note that we would write g of xyz as x squared plus y squared plus z squared minus 1, and the constraint is satisfied for every order triple xyz such that g of xyz equals 0. By the method of Lagrange multipliers, the optimum value is attained whenever the gradient of f is equal to the gradient of g multiplied by a scalar value lambda. This constant is what we call the Lagrange multiplier. The gradients consist of the partial derivative of the function, denoted here as f sub x, for the partial derivative of f with respect to x. Note that the partial derivative of f with respect to x is 2, while the partial derivative of g with respect to x is 2x. We do this for y and z as well to get the complete gradients. We can distribute the scalar factor in the right side to make this a vector-to-vector equality. The vectors look daunting, but this just means that each element should be equal. Hence, we can generate this system of equations. We can rewrite each equation in favor of x, y, and z. And if we let k equals 1 over 2 lambda, we actually get the same system of equations we got using CSI. Of course, we can solve this using the same way earlier to get k equals plus minus 1 over 7, and we use the same justification to say that k must be positive and x is equal to 2 over 7. Regardless of the method, we should get x equals 2 over 7. I'm leaving it up to you to decide which method you prefer. Hope you learned something today. Thank you for watching, and please subscribe for more content.